Okay, ideal gases should be a pretty straightforward chapter if you're taking chemistry as your other A-level subject. Okay, so let's first start with what is meant by an ideal gas. By definition, an ideal gas is a gas that obeys the equation PV over T equals to constant for all values of PV and T, where P is pressure, V is volume, and T is thermodynamic temperature. This definition is something that you would need to remember if you're asked to define what is the definition of an ideal gas. Sometimes it's worth 2 marks, sometimes it's worth 3 marks. If it's 3 marks, it's this entire statement here. Okay. Then when you say that PV over T is equals to constant, this is actually known as your general gas law, which can be rewritten as P1 V1 over T1 equals to P2 V2 over T2. Okay. Now, when you're talking about an ideal gas, you can make a real gas behave like an ideal gas provided that the temperature is very high and it is a very low pressure. Okay. Now, all values of T that you see in your ideal gas chapter here must be your thermodynamic temperature, meaning to say it must be your Kelvin temperature. Okay. And when you're talking about gases and you want to quantify the amount of substance of a particular gas, you have a particular quantity called amount of substance actually, which is measured in number of moles. Amount of substance is your physical quantity. Number of moles is actually your units. Okay. So when it comes to dealing with gases, there's a particular quantity that you often use to measure gas. That one is amount of substance, measured in moles. When we ask you what is 1 mole in your question, 1 mole is just simply the amount of substance that contains 6.02 times 10 power 23 number of particles, atoms, or molecules. Just use either one of these terms in your answers, that will do. Okay, so 1 mole is any substance that has an amount equal to 6.02 times 10 power 23. In some textbook, it's alternatively defined as the amount of substance that contains the same number of particles as there are 12 grams of carbon-12. Okay, so this one is also acceptable, but the first one here is actually the better one. And when you're talking about amount of substance, there's a particular constant that you would use a lot. That one is your Avogadro constant, Na. That is having a value of 6.02 times 10 power 23, which is actually the number of atoms contained in 12 grams of carbon-12. Okay, right? So Avogadro constant is this value. Is referring to the number of atoms contained in 12 grams of carbon-12. This is actually your 1 mole. Okay, 1 mole is actually equals to your Avogadro constant. And 1 mole, coincidentally, is the number of atoms contained in 12 grams of carbon-12. Okay. Next, you move on to your ideal gas equations. All right. Now, for your ideal gas equation, there are quite a number of equations that you will have to learn as well as their derivation. The most straightforward one that you will first learn is PV equals to nRT. Okay. Now, just now it was mentioned to you that for any ideal gas, the gas will obey PV over T equals to constant. Okay. Now, if you try to think a bit further, given any number of moles n of gas, because your constant PV over T is equals to constant, your PV over T equals to constant is actually going to be multiple of number of moles, regardless of the PV and T of the gas that you use. Okay, what we mean by that is something like this. Okay, this I think will be much easier to understand. If you just look at this first group of diagrams that I've just drawn for you, if you have 1 mole of gas, let's just say at one particular state, they are at P1, V1, T1. And then after that, I did something to the gas to change it to P2, V2, and T2. And then I did something again to the gas to change it to P3, V3, T3. Because it's an ideal gas, the PV over T for each of these states will be the same. Meaning to say P1 V1 over T1 will be equals to P2 V2 over T2 equals to P3 P3 over T3, which people actually found out will be equals to 1 R. Okay, this is the part where they say that it was constant. They say PV over T is equals to constant, and they found out that that value will always be equals to 1 R. If you then change the number of mole gases that you have, say to 2 moles, again, you have P1, V1, T1. You did something to the gas to change it to P2, V2, T2, and then you did something again to the gas to change it to P3, V3, T3. It's the same thing again. P1, V1 over T1 equals to P2, V2 over T2 equals to P3, V3 over T3. This entire thing would always remain constant. But then again, what people found out was that for this particular gas at 2 moles, those constant values that you have here would always be equals to 2R. So the next one would be this one. You see your number of moles is 4.5. You again have the gases at 3 different states, P1, V1, T1, P2, V2, T2, P3, V3, T3. What you can actually say is that P1, V1 over T1 will be equals to P2, V2 over T2 equals to P3, V3 over T3. Again, this is the part where they mean by constant. Okay, but specific for this number of moles at 4.5, they will say that all those constant values that you have here would actually be equals to 4.5 times of your molar gas constant. Okay, so it's because of this, when they look at these cases, they actually can generalize PV over T equals to N number of moles times your molar gas constant, such that you get PV equals to nRT. Okay, this is how they actually got your PV equals to nRT equation. Okay, this is actually the better explanation to explain why is it like that. If you recall that number of moles is number of gas molecules divided by your Avogadro constant, this PV equals to nRT that you have here, if you were to substitute in N into here, this is what you're going to get. You're going to get PV equals to N over NA times RT. What you want to then do subsequently is that you want to group these two constants together, the R and your NA together, so that you now get something like this. PV equals to N R over NA times T. So what you can actually say from here is this. R is a constant. NA is also a constant. So you can define a new constant from that where it is the ratio of R to NA. That new constant you define is called your Boltzmann constant. Okay, the Boltzmann constant, the symbol is K. It's the ratio of your molar gas constant to your Avogadro constant, giving you this value that you see on your notes. This is a value that you can actually get from your exam paper also. You don't need to memorize this value. Okay, so you need to know that there's another second equation, PV equals to NKT. And this one, the derivation is required. You need to know a bit of how is it derived. It's derived from the first equation in the first place. Okay. Okay, now if you move on to the next page, you have to go through something called kinetic theory of gases, which you may have learned before this. Now, for kinetic theory of gases, there are actually two sets of it. One that is for the basic assumption, another one is for the more important, more detailed assumptions. The basic assumptions of kinetic theory of ideal gases is that gas consists of particles called molecules. The total number of molecules is very large. These molecules are always in constant random motion and obeys Newton's law of motion, the first law, second law, and third law. And any pressure on the container that contains the gas is the result of the reaction on the walls as the molecules strike and rebound from the walls of the container. Okay, so this one here is something that you probably will have learned under IGCSE or SPM. They won't test you so much on this, But what they will test you regularly is the one in this table here, the more detailed important assumptions. So for kinetic theory of gases, they always assume that there is no intermolecular forces between the gases. Okay, there are no intermolecular forces between the gases. And then the next thing they assume is that the total volume of your gas molecules is actually negligible compared to the volume occupied by the gas. Okay, so what do we mean by that is something like this. If you imagine that you have a container like this, and then this one is your gas molecules. This one are your gas molecules. 1, 2, 3, 4, 5. If you were to add up the volume of the gas molecules themselves, you probably add up to about this size. This one is your volume of gas molecules. Let me just write it out. This part here is your volume of gas molecules. And then this part here is your volume of container. So if you were to compare the volume of your gas molecules with the volume of your container, the volume of your gas molecules is actually negligibly small compared to the volume of your container. Here, I did not write it as volume of your container. I wrote it as volume occupied by your gas. It's actually the same thing. Okay, so this one I probably should write it as volume of container. Okay, so this is the second assumption under kinetic theory of gases. And then the third assumption of kinetic theory of gases is this. Your molecules are always in random motion. When we say that your molecules are in random motion, it means that they move in all possible directions with different speeds. Okay, random actually means all possible directions with different speeds. Okay, and the fourth assumption that you will need to remember is this one. Collisions of the gas molecules with each other and the walls are always elastic, so that the molecules actually move with uniform velocity before and after collision. Uniform velocity here means constant velocity. Okay, so again, what do I mean by that? If you imagine that this one is your container again, the volume that is containing your gas molecule, you have one gas molecule that moves towards the right with a speed of v. It will obviously hit the wall, and then after that it will rebound. But because the collision is elastic, what will happen is that when your molecules rebound, it should rebound back with the same speed v. That's what this statement here is actually trying to tell you. Your collisions are always elastic, so that when they rebound after collision, you're still having the same velocity. Okay, so that is one assumption here to remember. And then the last assumption that you also need to remember is this. They tell you that the time of collision is negligible compared to the time between collisions. Okay, so what does this mean? When you look at your gas molecule again, maybe I use back this same diagram that I've drawn here. Your gas molecule initially it hit this wall, this collision with the wall, and then it will rebound. So once it rebounds, just like I mentioned to you, it will rebound back with the same velocity. So it will continue to move until it hits the next wall. Okay, and because it hits the next wall here, there's another collision here where your molecule will again rebound the other way now. Okay, so that it now hits back this wall, so that you now have another collision here. Okay, so when you're talking about time between collisions right now, that's being mentioned inside the notes, it's actually referring to you going from here to here back to here. The blue colored section that I just highlighted. This is what you call as time between collisions, or you can think of it as the time it takes for a gas molecule to hit the same wall again after rebounding from it. Okay, this is what you call as time between collisions. For time of collision itself, is actually just referring to this portion here. This is time of collision. Okay, so when you compare time between collisions with time of collision is actually negligible compared to time between collisions. This is another assumption. Now, why do you need to assume this is so that you can derive another equation for ideal gas later? Okay, so that one will actually be covered under page 4.